So this is the second video of a very simple introduction of finite element method. In particular, we showed that the problem that we've been solving by finite difference, namely f negative u double prime is equal to f, u0 is equal to u1 is equal to 0, that we call it problem D. That's equivalent to find u in the space W such that u prime v prime is equal to fv. The parenthesis here means the integration. You multiply them, multiply u prime v prime, integrate, or you multiply v and u and integrate. W is defined to be a function, or the function u's from 0, 1 to a real valued function. It's continuous, and the u prime is piecewise continuous. Okay? So we call that problem V. So the problem V is actually the starting point of FEM, so-called variational formulation. So what to do is that we think about the space W. Okay, the space W, and this W is a collection of functions. Okay, if we take a look at the function, let's say like this, okay, and we know it has satisfied the boundary condition, so we should have added u0 is equal to u1 is equal to 0, right, in this definition of the W. And 0, 1, there's one such function, and we're not going to study the continuous function. In numerical analysis, we have to discretize things. In particular, if we discretize the domain 0 to 1, in this case, maybe by 5 points. Okay, so m plus 1 is 4, m is 3. So basically, you look at here, you look at a few points on the function, and you evaluate its function value at those points and then connect the straight line. Basically, in interpolation, we interpolate this by a piecewise linear function. Okay, so which means here we're going to add a few more points for a total of 7 interior points, 1, 2, 3, 4, 5, 6, 7, and then one last point. Okay, so you have like functions like this is a piecewise linear. Alright, this kind of function. The point is that as you increase m, so here m plus 1 is equal to 1, 2, 3, 4, 5, 6, 7, 8. Remember what we meant by is that this is x0, this is xm plus 1. Okay. As you increase m, the red piecewise straight line is going to get closer and closer to that sine curve, right? So it's getting more and more accurate. So this function is a So this red function, this piecewise linear function, is a reasonably accurate approximation to the curve. Another observation is that which basically the hint is that the space W can be approximated by a space of piecewise linear. Take a look at each piece is linear. Piecewise linear functions on the domain 0 to 1, okay? So we try to approximate the W because otherwise we cannot really quantify the W. We cannot really use numerical schemes to attack the problem. Another observation is that if we look at fewer points, okay, if let's say we only have 3 points, okay, and we look at a function which is equal to 1 here, and then 1.5 there, okay. So it's 1.5, and then 0. So here is 1.5. Is as at x1, x2, right? And I want to say this is equal to a 1 times this function, the same. I'm just plotting them, the same domain x1, x2. Function is equal to 1 at x1 and 0 everywhere else. Okay. Plus 1.5 times the second function, which is x1, x2, is equal to, now this function is equal to 1 at x2, and then quickly going to 0 for the neighboring points. So this is like a tent. This tent function at x1, right? This is tent at x2, okay? So this function is actually equal to 1 times the first tent function plus 1.5 times second function. It's easy to see because we know that they are both piecewise linear, okay? The left-hand side is piecewise linear, the right-hand side is piecewise linear. And if it's piecewise linear, at each segment, the function is determined by the 2 point values. And we know if this is f, that is g. We know that number 1, f at x1 is equal to 1, right? And then we know g of x1 is equal to, if we call the first part, so if we call this phi1, this phi2, okay, we know g is equal to 1 times phi1 plus 1.5 times phi2, the whole function evaluated at x1. So this is phi1 x1 plus 1.5 times phi2 x1. We know phi1 x1 is equal to 1, and phi2 x1 we know is 0 by design. So this is just equal to 1, right? And then if you look at f of x2, we know this is 1.5. Here, g of x2 is same function, phi1 plus 1.5 phi2. Now evaluate x2. This time, phi1 evaluated at x2 is 0, but phi2 evaluated at x2 is 1. So this is get 1.5. So two piecewise linear functions, they match at the nodal points. They must be the same. Okay. So this is tricky. Think about this. If it's this first time you are seeing this, think about this funny phenomenon for a while. You can write a piecewise linear function as a linear combination of a bunch of tangent functions. So let this sink for a while. So in general, given the mesh, right? What we have been using is x0, x1, x2, all the way to xm plus 1. All right. We can define m tanh functions. All right, at any xi is equal to 1, and then at xi minus 1 is 0, and xi plus 1 is 0, right? This is phi. So phi of x is equal to 1 at xi, 0 at xj when j is not equal to I, right? And it's also it is piecewise linear. Okay, so we sort of have a moving tanh, right? So we have this guy, and then we have a tanh. This is 0 as well, and now it's 0 here, there, and all the way till the end. We have m such tanh functions. Okay. And as we argued, W this can be approximated by a space of piecewise linear functions. In the meantime, we just showed that the piecewise linear can be written as a linear combination of those tanh functions. In other words, this is basically a span of that phi1, phi2, all the way to phi m. What do we mean by a span? Span of f and g. This is a linear combination is af of x plus b g of x for any a b. All right. So this is like a summation of a I phi I of x. Now I is from 1 to m, and this ai is any real number. Okay. So any such function, as we just saw, a piecewise linear function can be written. So here, okay, this guy. A piecewise linear function can be written as a linear combination of two tanhs. So any piecewise linear function can be written as a linear combination of these m tanh functions on the mesh x0, x1, all the way to xm plus 1. Once we have that, we can change the problem V is a continuous problem to a discretized problem VH. Okay, and we call this space WH. H for discretization. H is like 1 over m plus 1. Okay, so which is we find U. Okay, we find now UH to denote approximation. We find UH in the space WH such that the integral of UH prime V prime is equal to FV for any V in the space WH. Okay, we call this problem V sub H. It's discretized V. Alright. The idea now is simple. If you tell me, so UH in the space WH, so basically UH is piecewise linear. We either we use that span space definition, or we go like the following, which we don't use the span definition now. is piecewise linear, right? Which means UH is determined by its point values at x1, x2, all the way to xm, right? If you tell me the point value, and then you know it's piecewise linear, so just connect the points, the point values, all right? So, so which means this UH, right? This unknown UH, you find such a UH in the space W. This UH of X is actually equal to UH at X1 times that phi1X plus UH at X2 times phi2X plus UH at XM times phi mx. Okay? Phi mx. And so finding UH in such a space WH is equivalent to finding the point values of UH at those nodes. Okay? But the trick here is that we think of this as unknowns. Meaning we don't know the value. For the brevity of notation, we're going to call this A1, A2, here is AM. Okay? So basically, we write UH as a summation from I from 1 to M of A, I, phi I of X. Okay? So we just call the function value UH at xi by a different name, AI. They are the same. Alright, once we have this, so again, let it sink for a while, and now we need to solve for UH. So UH satisfies, remember, UH of X satisfies a problem VH, meaning that my UH, which we know now is summation of AI phi I of X, right? Here I is from 1 to M. H, this is integrated with U prime is equal to that F, the right hand side function, F V. Okay? This should be true for any V in that space WH. Piecewise function. Okay, piecewise linear function. WH. So in particular, if you tell me these two integrals are the same, okay, the two integrals, i.e., this, remember the parenthesis means integration, i.e., if we integrate I from 1 to M of AI phi I, here is phi I prime, is U prime, so phi I prime, of X, this whole thing multiplied with Vx, integrated with X, this is equal to F of X, V of X, dx, okay? If you tell me those two integrals are true for any V, in particular, it is true for V to be equal to Vj, those 10 functions, for any j, right? So then let's see what happens if you go through all the j's, basically. Okay? And that's a trick. So when V is a phi1 and V is phi2 and so on and so forth. When V is phi1, what we have is that we have the summation I from 1 to M of AI phi I prime of X, right? This is phi1 prime of X. That's equal to F phi1 of X, right? And when it's 2, we have this sum AI phi I prime x, this with phi 2 prime x, this is equal to f with phi 2x, right? This integral is a linear function with the first part. So we can, in particular, we can write down the integral of the sum is the sum of integrals, and then the AI is constant. AI has no x in it, so we can move out the AI. So this is like summation of I from 1 to m, AI, and then we have phi I prime, and then phi 1 prime. This is equal to f phi 1x. Okay. Now the trick is to write this as linear algebra equations. Okay, and we write the AI here, it's the unknown, so it's A1, A2, all the way to AM minus 1, AM, which are again just function values of UH unknowns. And this is the first equation, the equation we just had. Okay, so AI hit with A1 hit was phi 1 prime, phi 1 prime, right? A2 is phi 2 prime, phi 1 prime here, and then all the way to phi m prime, phi 1 prime. All right. So this is our first row. Okay. And similarly, the second equation becomes the second row. So we are going to have phi 1 prime, phi 2 prime, and phi 2 prime, phi 2 prime, all the way to phi m prime, phi 2 prime. And that's nothing but our second equation. Okay? If we continue, if we let our j to be m, we get that this is phi 1 prime with phi m prime, phi 2 prime with phi m prime, all the way to phi m prime with phi m prime. The right hand side, that's f with v, so the first equation is f with phi 1, f with phi 2, all the way to f with phi m. Okay? Let's finish it here. So the v is phi 2. You can write down the integral of sum as sum of integrals, and then move out as constants. The same idea, phi I prime of x. This is phi 2 prime is equal to f with phi 2x. Okay? That's again our second equation. Same thing goes on and on to the last one when j is m. So if we call this matrix A, so we have, like the finite difference case, we have a matrix A times a vector A1 to AM, and this is equal to the right hand side, which is f phi 1 all the way to f phi m, right? And the matrix A, its component is A sub ij, and with ij, ith row, jth column is phi j prime, phi I prime, all right? Ith row, the first row, they all have phi 1 prime as the second component of this integral, so it's phi I prime in the back, and then phi j prime as the first. Okay? And let's try to compute this matrix and see what it is. Okay, for that, we need to evaluate. So the Aij, again, is the phi j prime with phi I prime, which we know is the integral of 0 to 1, phi I prime times phi j prime dx, all right? So for that, we need to calculate what is phi I prime equal to, all right? And we recall that phi I prime is at xi is equal to 1, and then it goes to 0. It's a tent. Okay, this is for phi I. So phi I prime, we clearly just take the derivative. Okay, here is xi minus 1, here is xi plus 1. The derivative is the slope. Okay, what's the slope? We know the little segment here is h. So we know phi I prime, this is equal to 1 over h, when x is between xi minus 1 and xi, okay? And when x is between xi and xi plus 1, this is negative 1 over h, it's with negative slope. The slope is rise over run, and it's 0 when x is less than xi minus 1 or x is larger than xi plus 1, alright? So that's our phi I prime. So which means we can calculate aij, alright? So the aii, in particular aii, when I is equal to j, this is the integral of phi I prime times phi I prime dx, okay? And this function time itself, and it's only non-zero between, so in this case it's only non-zero between xi minus 1 and xi plus 1, alright? So that's like phi I prime of x squared dx, okay? So is 1 over h, the function value is 1 over h times 1 squared, or negative 1 over h squared. In both cases, is equal to 1 over h squared times, this is the function value times the interval, right? The area. The integral of this is area times the width of this rectangle 2h. So we get, this is 2 over h. Okay? So another observation is that if I minus j absolute value is larger than 1, then aij is equal to, so that's like phi I prime with phi I plus 2 prime. Alright, so this is like if you have here this guy, the guy's right here, okay, versus here is I, so here is I plus 1. If we move one more to the right, here's I plus 2. So this guy is like this. Then if you integrate at any interval, one of them is 0. Okay, there's no overlap. So the mathematical name is the support. The supports of the two functions has no overlap. So you cannot find one interval so that they are both not 0. Alright, neither of them is 0. So either phi I 0 or phi j 0. In other words, for the area, for the places where phi I is not 0, phi j is 0. For the places where phi j is not 0, phi I is 0. So the product is always 0. So it's just equal to 0. Okay? And when the only other cases is that they are exactly equal to 1, alright? So ij are integers, so either they are the same, or when they are not the same, the difference is equal to 1 or is larger than 1, okay? So this is, think of this as j, aij. So they think of this as when j is equal to I plus minus 1, okay? So plus minus 1. So this is the case. Here is this case, right? Here is case is I with its immediate neighbor. Okay. So here is I here is I plus 1. So you have one function goes like this, okay, and the other function goes like this. Alright, so the only interval that the product is not zero, right? For the product to be non-zero, they both have to be non-zero. So the only interval that the non-zero is only from if 0 to 1, but the only place they are non-zero is between xi and xi plus 1. Okay, so this is a interval where the product is not zero. Okay, so it's easy to see. So it's phi prime, phi j prime dx, and on that common interval, you always have a different sign. So this is like, okay, one guy is 1 of h, the other guy must be negative 1 of h. Okay, so this is the function value times the width, which is not 2h but h. Okay, so you get this negative 1 of h. So we know this guy is either equal to 2 of h or 0 or 1 of h. Okay. Once we have this, we can see that, well, this matrix A, when AII we factor out 1 of h. Okay. The AII are the main diagonals. When I is 1 is A1 1, A2 2, A3 3, and so on and so forth. They're all equal to 2. Okay. When ij, the difference is 1, meaning is I plus 1, so it's 1 2, is or 2 1, right? 2 3 or 3 2. So at those places it's negative 1, negative 1, negative 1, negative 1, and so on and so forth. Okay. So by now, and all the rest is 0. Okay. By now you can probably recognize this matrix. This is actually identical, other than the factor of 1 over h squared from the finite difference. Recall, for the FDM matrix A, right, we had this 1 over h squared, 2, 2, negative 1, negative 1. They are identical. Alright? And we're basically multiplying both sides of finite difference equation by h. So 1 over h squared becomes 1 over h, and the right hand side is there's also a factor of h. So by solving this equation with this matrix, you obtain the function value. You obtain the unknown values a1, a2, all the way to am. So solve the vector a1 to am, you get f phi1, f phi m. Solve that, you get the values of a1 to am, which again is point values of UH, right, at the grid points xi. So it's similar to the finite difference. You assume the value and then you solve for them. So for this particular case, the finite element is equivalent to the finite difference in